Okay, so welcome back. This is section 7.5, conditional probability, and tied to that are the idea of independent events. All right, in this section, we're going to take a look at the idea of conditional probability. We're going to find a product rule for probability and talk about independent events. All right, so start off with, what is conditional probability? So up till now, we've been dealing with probability of something happening, probability of something happening, probability of something happening. In this section, we're going to take a look at conditional probability, which is going to talk about not something, but the probability of two things, or possibly more, happening. But we're going to think of this in terms of a time sequence. Like something is going to happen, some event E will happen, and then some event F will happen. And what we're going to look at is we're going to ask the question is, if two events are performed in succession, how does the outcome of the first event E affect the probabilities of that second event F? Now, the names for these two events, it doesn't matter. It's this idea of, if I know what happened first, how does that affect the probability of the second? If I know what the first card pick was, how does that affect the probability of the second card? Things like that. Okay. All right, so the first example we're going to take a look at for conditional probability is this one. This is a empirical conditional probability because we have data. Okay? And so what we have here is we have a table of data. The Midtown Bank has found that most customers at the teller's window either cash a check or make a deposit. And the following table indicates the transactions for one day. And so if you take a look at how this table is laid out, these four numbers that I'm going to highlight here in blue are the number of people who performed the given event. And what I mean by that is each of these numbers, like this 60, it isn't just one thing. It's actually a combination of two things. It's a person who made a deposit and also cashed a check. And this 10 down here, that's someone who didn't make a deposit and didn't cash a check. Okay? The table also has some values down here, this 90 and this 30. And those 90s and 30s are the sum, the totals, for the people who cash checks. So there are 90 people who cash checks, and who didn't cash checks, that's 30. They also have some sums over here on the right, an 80 and a 40, and that 80 would be the total number of people who made a deposit, and then the 40 would be the total number of people who didn't make a deposit. And then we got a number down there in that right-hand corner. Let's see, we'll use yellow for that. And that one is what is that going to be? That's the total number of people who either cashed a check or made a deposit or did some combination of those things. So in terms of the experiment, that's that total number n. That's our sample space that we're working with here. All right, so here's the questions that we're going to ask. We're going to ask things like this over here on the right. We're going to say, how does knowing if an individual does or does not make a deposit or does or does not cash a check affect the probability of performing the other act? That is, if I know about their check cashing, how does that affect their deposit making? Or if I know about their deposit making, how does it affect their check cashing? Right? And so if we let C be the event cash check, and we let D be the event make a deposit, well, I know from basic probability, the probability of C, that is the probability that they cashed a check, is going to be a fraction. My denominator is going to be 120 because there are 120 people who came into the bank. And my numerator is going to be 90 because there are 90 people who cashed a check. And then, of course, I reduce that. That reduces down to what? 9/12, which goes down to what? 3/4. Right, so 75% of people who walked into this bank cashed a check. It's the 90 people who cashed a check. And I also know that the probability that someone made a deposit is going to be the fraction. My denominator is going to be 120 because there are 120 people who came into the bank that day. My numerator needs to be the number of people who made a deposit. There were 80 people who made a deposit, right? And so I get that the probability that someone makes a deposit is going to be 80 out of 120. That's what, 8 out of 12? Which is what is that going to be? 4 goes into both of those twice up top, and 3 times 2/3. Okay? But now let's look at the conditional probabilities. Okay? Conditional probability, here I'm going to give you the definition. The conditional probability of an event E, given that event F has already happened, and we write it this way. Okay, so I want to take a look at that right there real quick. You'll notice that we've got a probability and we have a line in the middle. This one that goes on the left is the future thing that we're calculating the probability of. This one is the past thing, the thing that we know how it turned out. So when I write an E over here and an F over here, I'm saying what's the probability that E occurs if I know the outcome of F? Right? And so we're going to ask things like, what's the probability that you cashed a check if we know that you made a deposit? So then the left-hand side over thing here would be the cash a check, and this would be that you made a deposit. Right? And the way that we calculate this probability is we take the probability of the intersection of the two events divided by the probability of the event that we know occurred. Right? Now, of course, because we're doing division here, the probability of F can't be 0, otherwise this whole thing is dumb, because you can't divide by 0. All right. So let's take a look at what's being asked down here in this table. We'll take a look at this first one down here, probably a C given D, and it looks like I don't know if I gave myself enough space here, but maybe I did. Okay, if I just go straight from a formula, the probability of C given D is going to be the probability of C intersection D divided by the probability of D. Now I already know the probability of D. The probability of D is going to be that 2/3, right? That's what we found. We found that up over here, right? And then probability of C intersection D. What does that mean, C intersection D? Well, C intersection D. C was cash a check. D was make a deposit. So that's the people who cashed a check and made a deposit. Now up here in this table, who cashed a check and made a deposit? It's those 60 people. And so then that would be 60 out of 120. And so my numerator is going to be 60 out of 120, and I clearly did not give myself enough space here, but I need to simplify that, so I'm going to grab my calculator, and I'm going to say, oh, mighty gods of the TI. 60, this needs to move, divided by 120 over 2 divided by 3, 0.75, or if I want it as a fraction, I get 3/4. And so I say that this is equal to 3/4. So the probability that an individual cashes a check, given that we know they made a deposit, is 3/4. Okay? Now, this is the formula way to do this. There's also another way to do this, another way to look at this. Right? Essentially, what conditional probability does is conditional probability reduces our sample space. So I'm going to go ahead and erase this. And I'm going to say there's a different way, not a better way, not a right or more correct way, but just a different way to solve this problem is to use numerical values. The number in the intersection of C and D, just divided by the number in D. Because I have data, because I have numbers, I can do it this way as well. I have to use this formula if I only have probabilities, but I can use this formula, the one I'm looking at here, if I have numerical values. So I'm going to go up to my table and I'm going to ask myself, I don't want that there, I want the blue marker back, there we go. How many people are in the cash to check and made a deposit? Well, cash and check and made a deposit is at 60. And then how many people made a deposit? Well, that would be that 80 right there. And so 60 over 80, and if you do a little bit of math and reduce, that's going to be our 3/4. So I've got a formula way with probabilities, and I got a formula way with numbers, and it all depends on what kind of information has been given to me. How was the information delivered to me? Do I want to use numbers? Do I want to use formulas? Right? All right, so let's take a look at this one over here on the right. Now, I got the same letters, but we just did CD and this one's DC, so what is the difference? So before I even start calculating probabilities, I want to take a look and see if I can figure out what it's asking. In this example right here, the future event is cash a check. The past event is made a deposit. So we're calculating the probability that they will cash a check in the future being a relative term here, not like next week, but like in their trip to the bank, if we know that they made a deposit at the bank. This one over here flips that narrative and says, what's the probability that the future event will be make a deposit if we know that they cashed a check? Right. And so I'm going to use the number way because I've got the numbers up there. So this is going to be the number of elements in deposit intersect cash a check divided by the number of elements in the cash a check. Right. So I'm going to go with my table. I'm going to say, okay, how many people are in the deposit and cash a check? Well, that's going to be that 60 that we used. And then how many people are in the cash a check pile? Well, that's going to be this 90 right here. And so that's going to be 60 divided by 90. 60 divided by 90 is 2/3. All right. So I'm calculating conditional probabilities. Right? I got another conditional probability down here, over here on the left at the bottom. And what is this one asking? Well, if I read it mathematically, I would say, find the probability that the complement of C occurs given that D occurred. Or the number of people who did not cash a check and made a deposit just divided by the number of people who made a deposit. So the number of people who did not cash a check, that's 20, and made a deposit. So that's 20 divided by the number of people who made a deposit, that's 80. That's 20 out of 80, that's 1/4. Right. Now I absolutely could be using this formula for all of these, but to use that formula, I'd have to calculate all these probabilities and then put those probabilities into the formula. I'd rather just use the number formula. That makes it easier. All right, last one, I've got the probability of C given D complement. So the probability that they will cash a check and given that they did not make a deposit. So it's going to be the number of elements in the intersection of cash a check and didn't make a deposit divided by the number of elements in didn't make a deposit. So I go back up to the table. Cashed a check and did not make a deposit. Cashed a check and no deposits right there. That's that 30. Divided by did not make a deposit. That's that 40. And that reduces down to 3/4. All right, we're at like 13 minutes, so I might just call it right there, make a second video, follow this up. But we are in session 7.5. We are taking a look at the idea of conditional probability. Conditional probability is asking the question, if I have two things happening in a time sequence, what's the probability of the second occurring if I know the outcome of the first event? Okay, so our cashing checks, make a deposit idea here is, what's the probability that they will do this action at the bank if I know that they did this other action at the bank? Okay? I'll see you all back here for part 2.